Welcome to the beam analysis in GSA tutorial. In this tutorial, you're going to learn how to build a simple beam model in GSA, make use of load combinations, obtain bending demands, shear demands, and beam deflections. In order to illustrate this, I'm going to follow an example that you can find in your beam analysis and design theory handout. The first thing that we need to do is to create a new file, so we're going to go to File, New. This window will pop up. It essentially enables you to input information about your project. This does not influence your result in any way, so you do not have to complete this information if you don't wish to. If you click on Next, the next thing we're going to do is define the type of structure. We're looking at a plane structure, and we're going to select kilonewton meters for our units. You can click on Finish, and when this window pops up, it says, do you want the initial current grid set to an appropriate non-global grid? You can ignore this for the time being and just click on No. The first thing that we're going to do is to define our beam cross-section properties. We're going to do this via the gateway menu, which you see here to the left. So we're going to go to Properties, Section Properties. This window will pop up. If you right-click on the first white cell and go to Wizard, this window will pop up. It essentially enables you to define or name your section property. I'm going to call it steel beam. You want to make sure that you're selecting the relevant material property for your beam element. In this case, steel is what we want. And we're going to select a section from a catalog, so you can go to Definition Method, Catalog, click on Next. The catalog type that we're interested in using in this case is Europrofile. The type of section is HE beam. And now I can select the relevant section for my example, which is HE300AA. So if you scroll down, it should be listed here, and you can find it under HE300AA. The next window is just checking the relevant section sizes, which are essentially being imported from this catalog, and you can verify these and click on Finish. This essentially inputs that section information into the table. And at this point, we've finished defining the cross-section properties for our beam. The next thing we're going to do is to define our nodal coordinates. So we're going to do this also through the gateway menu. We're going to go to Nodes, Coordinates. We only need two nodes to define the geometry of our beam. The first node is going to be located at 0, 0. The second node is going to be located at 7, 0. In this case, 7, 0 because we have a beam with a span of 7 meters. If you had a beam with a span of 10 meters, your second node would be located at 10, 0. You can see that this illustrates two red dots at the location where those nodes have been defined. You can check that the node numbers are correct by turning on the label node numbers using this shortcut to illustrate them. So you have node 1 and node 2. And the next thing we're going to do is actually define the element itself. So we're going to do that by clicking on the toolbar shortcut Add Element Sculpt Tool. And then once we've selected or clicked on that, we can essentially connect node 1 and node 2, and you can see that this will essentially draw a line to represent our beam element. You can also verify the beam element number by turning on label element numbers, and you can see that this is beam 1. The red dots that were representing the nodes are no longer present since these are now being connected to define that beam element, but you can still illustrate visually the nodes by clicking on label node dots, and you'll essentially have a little dot wherever there is a node in your analysis model. The other thing that we can do is to display the cross-section. So you can click on Section Display, and if you now rotate the beam, you can essentially visually check that the cross-section is as you intended it to be. This is a type of cross-section that we're interested in using. So after doing that visual check, I can turn off the section display. At this point, I'm also going to turn off the node numbers and the display or label node dots, and I'm going to go back to my Y elevation. The next step is to generate supports. We've defined the overall geometry of the beam and the cross-section properties, but we have not yet defined the support condition for this beam. We're going to do this via the gateway menu, so you can go to Nodes, Restraints, and we're going to effectively have a pin on the left of the beam, so node 1 restraining displacement in the X and in the Z direction, and we're going to have a roller in node 2 effectively restraining movement in the Z direction. This is something that you can also visually check by labeling restraints, and you can see we have a pin on the left and we're restraining movement in the set direction on the right, effectively restraining movement in the up and down, so essentially we have a roller on the right. The next thing we're going to do is to define the load cases. We're going to go ahead and do this via the gateway menu again. You can go to cases and tasks, and you can go to load case specification. We're going to define two types of loads. We're going to define first permanent loads or dead loads. The type of load we can say is dead, and then we're going to define the variable loads, and we can define this case type as live. The definition of dead and live won't have an impact on your overall results. It's just for bookkeeping, but we want to put this information if it's something that will enable us to double check the type of loads that we're using in our analysis, so it's good for bookkeeping. The next thing we're going to do is to actually define the beam loads. Again, we're going to do this through the gateway menu. So we're going to go to loading, beam loading, and then beam loads. In the beam list, we could say that we want this load to be applied to beam element 1, so we could type in 1, but we can also just type all, and it would apply the load to all beam elements in your model. In this case, we only have 1, so we get the same result whether we type in all or just 1. The first load that I want to define is a permanent load. It's a uniformly distributed load. I want it to be defined in the global axis and in the set direction. The actual value of load that I'm interested in inputting is 3 kilonewton-meters facing downward, so that's why I'm going to have a minus sign. And I'm now going to define the second type of load. I'm going to select, again, all beam elements, variable load in this case, a uniform load on the beam, global axis definition, set direction, and now the type of load or the value of load that I want to input is minus 6. These loads are something we can also visually check. The minus sign, as you can see, is relevant in this case because we want our forces to go downwards, and the set positive direction is upward, hence why I've been inputting the minus sign. You can also visually check the loading values are correct by clicking on all load diagrams, and then you can select the case type from the pull down menu on cases, so we can look at permanent load and we can actually annotate this diagram to make sure it has the right values. So if you click on annotate or select for annotation, and you draw this over the load diagram, you can see that we have a minus 3, and if we change this to the variable load, we have a minus 6. So we're essentially visually checked that we're inputting the right types of loads into our beam problem. The next thing we're going to do is to define the combination cases. So we're going to have these permanent and variable loads combined in different ways. We're going to do this through the gateway menu. We're going to go to combination cases. So gateway menu, cases and tasks, combination cases. So the first combination case, I'm simply going to call it factored loads. This is the combination case that we're going to use to check for strength demands in bending and in shear. And the combination case that I'm interested in using is 1.35 times the permanent load and 1.5 times the variable load. So I'm going to say 1.35. The permanent load case is the first load case that we defined, and this is represented by A1. So 1.35 A1 plus 1.5 A2, because A2 is the variable load that we defined. This is essentially something that we can double check. So A1, I'm assuming it is the permanent load, and A2 is the variable load. If I go to the load case specification, I can see that A1 is what we define as permanent, and A2 is what we define as variable. So in this case, that is correct. If it were the other way around, and you had defined the variable in the first in the first row and then the permanent in the second row, then when you define the combination cases, it should be 1.35a2 plus 1.5a1. So just make sure when you're defining your combination cases that you cross-reference the load case specification to ensure that you're combining the loads in the correct way. The next combination case that I'm going to define is the unfactored loads, and this is what we're going to use to check overall deflections in our beam. Our factors are essentially 1, so we can just do A1 plus A2, and that would essentially combine the permanent and the variable loads without any additional factors. So we have now finished defining the combination cases, so at this point we're essentially ready to run our analysis, and we can do so by clicking on the shortcut Analyze All. Very simple model, runs very quickly, 0.125 seconds to complete the analysis. No errors, no warning, simple and straightforward. Now what we can do is essentially extract the information that we need for our given beam in order to conduct design checks. So the first thing that we're going to look at is the overall deflected shape. You can display this by clicking on Deform Image. You can also display the deformation displacement diagram by clicking on the displacement diagram shortcut. And if you want to annotate or see what values these are, you can also just select for annotation and drag this over, and I'll show you the overall values of deflection. When looking at deflection checks, we want to look at not the permanent by itself, not the variable by itself. We want to look at the combination of the unfactored load. So if we look at the unfactored loads, we essentially have an overall deflection of 10.32. This is very close to what we had obtained by hand calculations, where we had an overall deflection of 9.7 millimeters. The reason for these results being slightly different, though they're essentially very, very close, is that our hand calculations only considered bending deformations in the estimate of the deflection, whereas the GSA model is considering both bending and shear deformations. Don't worry about this for now. This is something that you will learn later on in your degree. The next thing that we can now do after checking and obtaining the deformation in our beam is look at the shear demands and look at the bending moment demands. So I'm going to turn off the deflected shape, I'm going to turn off the deformation diagram, and I'm now going to turn on the shear diagram. So I'm going to click on shear force diagram. In this case, I'm now interested in showing the factored loads because we're checking strength demands, and I can also select for annotation. We obtain a maximum value of shear at the support, at either support of 45.67. This coincides with what we had obtained via hand calculations. So we're verifying our hand calcs with this GSA model, or vice versa. And the next thing we can do is also look at the bending moment diagram. This is a type of shape that we're interested in, or we thought we would expect for a simply supported beam. If the diagram appears to be small and you want to double the size, you can use this shortcut. And again, you can also use the opposite one if you want to half the size of the diagram. We can select for annotation, and we can see that we have a maximum bending moment value at midspan of 79.93 kilonewton meters. This coincides with our hand calculations. You'll note that where we're expecting to see a zero moment at the supports, we're essentially seeing a zero value. It's actually shown as minus 1.8 e to the negative 6. This is because of the numeric format display. So if you click on numeric format and then click on decimal, then you'll see the 0.0, and then you just can check that you have zero moments where you expect to have zero moments, which in the case of the simply supported beam, it would be at the supports because there's no moment restraint at those locations. The next thing you can also do is obtain the reactions. This can be done by clicking on the reaction diagrams. We expect to see the same value of reaction at either end, essentially coinciding with the value of shear, and we can validate these results or check against our hand calculations. One other thing that we can do is essentially illustrate all of these results via contour plots. So you're essentially obtaining the same information but just displaying it in a slightly different way. I'm going to move this back out. so it's not in the way. And the way we would do this is by clicking on contour settings. If we want to look, for instance, at overall deflections, you can click on beam, spring, element results, beam, spring, displacements, and let's say displacement in the set direction. I would also suggest you click on contours based on actual values. It will set the contours based on the actual parameters or the numbers that that you're trying to plot, as opposed to some general or automatically set contour values. So if you click on OK, and again, when looking at deflections, we want to look at unfactored loads, you can see that we have the exact same results at midspan as we did when we displayed it in the other method. So it's just a different way of displaying the same results. We can similarly look at beam, spring forces, and moment. So we can go to the shear force in the set direction, click on OK. We want to look at factored loads because these are strength demands, and you can see that we have the same values either end. So these coincide with our hand calcs, and we could do the same if we wanted to with the bending moment. So we can go to moment MYY, click on OK, and again, same value of midspan that we displayed previously. If you wanted to display both diagrams simultaneously, that's something that you could also do, but you're essentially, just illustrating the same type of information. So this is the end of this GSA tutorial.